Okay, so so last time we talked about the general computer programming. We talk about import processes and outputs, and we also talk about the comments and the white space used in Java. Java used two type of comments. One is used the double forward slash. So this is basically just for put a small comment in a particular line. So you can at the end of the line or in the middle of the line you can put the double forward slash and put some of the comments. Or if you want to put a very big comments, um, the comment's gonna take a couple of lines. Then you can use the multi-line comments. So in which you can use the forward slash plus the asterisk, and then to close it, you can you use the asterisk and the forward slash. So this is actually the uh, multi multi-line comments. Uh, I mentioned that the comments is so important. You know, even though from compiler perspective, the compiler gonna skip the comments. So that means no matter how long, how big your comment is gonna be, the compiler gonna choose to ignore the comments. So the comment is actually designed for people to read. You probably think, well, if the compiler doesn't recognize why you need a comment, because all I need is I write the code so I can compile it so the computer can execute it. Uh, I have to say that the comments is so important. In many company, if you actually graduate, you find a job in most of the IT company. If you are one of the programmer or software engineer, you will find out many company, you know, in their actual project. If you actually join any group on any of the project, when you actually do the coding, you know, comments are mandatory. So the reason for this is because when you actually write the code, you probably understand the topics very well. So you can design, you can declare a couple of variables, you can, you know, write some kind of statements, you can define a couple of methods and in your code. Because you studied the problem very well. But when other people read your code, it will take some time. It's probably going to be difficult for people to understand why you want to do the problem like this. So in that case, comments is very important. And also in a company, because the teamwork is very important. So from company perspective, they don't want to relay a piece of code on a particular person, you know. So if you are the only person who create the code, who can understand the code, then what about if that person who create the code, he or she is sick, or he or she just left the company, leave the company, then that gonna be a nightmare. So from most of the business, they want to make sure that when you write the piece of code, someone else can understand it. So it just the ownership of the code cannot rely on a single person, for a project, because that's a disaster. If a project is rely on a particular person, if that person is has an issue, then the whole project are going to collapse. So that's the reason why they want the multiple people to you know to share or own a piece of code. So in that case, comments is actually mandatory in many companies. Also for the white space, in Java, white space is not really that important, because no matter how many white space you put in there, the compiler is simply going to ignore this white space. unless that white space is in the print statement. In the print statement, like something called string liberal. Okay. If you want to print something like I am Brady, then each space will be treated as a character. If you have two spaces, I'm sorry. If you have two spaces, then the Java can actually display two spaces or print out two spaces. So the white space will be, you know, but if the white space is actually in most of the statement in the Java code, they will be ignored. Okay. So and also error and warning. So we mentioned that you know it's unlikely that when you write a big program, you're not make a mistake. You always mistake is unavoidable if you actually create the code, a long code. So most of the mistake is going to be shown as the syntax error. So it's a syntax error. So that means you did not follow the syntax of the program, the code. Okay. The syntax is just like to the computer program, to the computer language. It's just like the grammar to the English language. So if you actually, in English, if you don't follow the grammar, sometimes you can understand it, but the meaning is kind of different. Okay. But in computer language, if you make a syntax error, then the compiler is simply going to say, there's a mistake, there's an error. Okay. So typically, the compiler going to generate a message when encountering a syntax error. And just keep that in mind. The compiler try as much as it can to guess what the error going to be. However, many times compiler cannot accurately point out what is the problem, because, for example, if the compiler say there's a problem in line 21, so then it's not necessary that the problem is actually the error actually happens in line 21. It's probably happened before line 21. And at the time when the error happens, the compiler may not recognize there's an error. But then after, the compiler continue to read the next couple of lines, they find out that something's not right. Okay. So then the compiler then realize, okay, something's right. So then the compiler going to point out, okay, there's an error at the line 21, but it actually not. So one of the example is like if you actually forgot the semicolon, which is kind of popular syntax error. Many people type the, the, the Java code and they forgot the semicolon at the very end of the line. So now it happens. It's a syntax error. But however, when a compiler reads the particular line, well, the semicolon is missing. The compiler may not immediately realize there's a problem here, but the compiler simply they believe that okay, if there's no semicolon, then I'm going to continue to read the next word. Remember, the compiler going to ignore most of the white space. So the compiler going to continue to read the next line and think the next line is part of the current line. So the compiler, and then the compiler realizes there must be something wrong here, but it will be confused and what was wrong. He may not be able to point out that there was error over here because you missed the semicolon. It will actually realize there's error until after a couple of lines, then the compiler realizes there's an error. So when you actually check the syntax error, then just check the line it just pointed out, and then check the lines before that. And also, when you actually see a whole bunch of error messages, don't be scared, because sometimes it's just caused by one error. because one of the error, it caused the follow-up errors. It's not really that many syntax errors. Okay. And I also mentioned the logical error is it's kind of tough many times, tough to diagnose, because the problem with logical error is that the compiler may not be able to catch it. So in that case, you think your code is perfect because it compiles doesn't point out any errors. But when you actually run it, you may experience an error. So that many times this is called a runtime error. Okay. So so logical error happens when you experience some kind of situation like something is divided by 0, or sometimes you don't have enough input to generate the output. There are a lot of, actually, it's kind of more like an internal problem. It's not the syntax. It's definitely not a syntax problem. So now, because of these syntax error, logical errors, a very, very good practice is when you actually you are doing the code, just try to compile as frequent as possible. So when you actually finish a couple of lines of code, then just compile it. Now, if there's an error, it's easy to fix the error because while the code is not big. So you can fix the error and then add a couple of more lines, then you just do the compiler again. Because if the compile error happens, at least you realize that the error is caused by some of the statement that was created after the last compile. Because last compile was when you actually compile last time, everything's okay. Then now you got a compile error. So you can narrow down when this mistakes happens. So that's why you need, it's a very good practice. Good practice is to compile and run frequently to avoid like overwhelmingly large number of compilation errors, because you say, okay, I do my coding very carefully, and I just write the one line, and after I finish 1,000 lines of Java code, I just compile, and then you suddenly find a lot of compile error. Then you don't know where to start. You have so many errors to fix. So which is not recommended approach. So I always believe that if you actually write a piece of code, compile it, and then add another piece of code, compile it, add another piece of code, compile it. So then this way you realize that if something goes wrong, it must be happened actually in the last couple of lines. Okay. Now in Java, there's also you may also see a compile warnings. The warnings is not error. It just give you it's still going to continue to compile. It's still going to run the code, and many times compiler warnings, it's just a warning. It never causes any problem. So it can complete the compiler, it can run the code correctly, but sometimes warnings actually may happen. Some of the warnings are very bad. It may eventually cause the runtime error. So it's actually the warning basically may caused by the logical errors, not the syntax error. And sometimes the warning is just warning. It's not a big problem. But a good practice is to write the program that compiles without warnings. Okay. Now here we just mentioned that if you try to compile the code and some of the warnings may not show up, So if you want to see the complete list of warning, if you use one of the compiler called Java C, then you can have an option to put the dash x xi int. Okay, then your code, your file. So that's I can show you if I got time today. So how to use this one, but you can use the Java C, which is actually the some kind of not a graphic compiler, but it's a command line based compiler called Java C. Okay. Now, so for the next section, I don't think I'm going to spend a lot of time on 1.5, the section 1.5. It's just basically talk about computers and programming. So we're going to talk about a little bit about the history of the computer programs. Okay. So now to understand how the programs works, you need to understand how the computer was created. You know, computer was actually, you know, it's the modern computer actually consists of a lot of chips, or are called integrated circuits. Okay. So integrated circuits contains a lot of small, what I can say, a unit, a small piece of small unit called switch. Okay. Switch is actually, you know, if you actually look at the switch, we actually we can see there are a lot of different switches we can see. Like if you actually turn on the light, turn off the light, so there's actually on and off. That's a switch, but that's basically a kind of physical switch. It's a device, you can actually see it. Now the switch in the computer actually circuit, which is actually all created in uh, a, a, a piece of like a wafer. So this circuits, this switch in the switch in this circuit is a kind of different. It's actually a switch that is controlled electronically. It's not actually controlled by your hand, just up and down. So you can turn the light on, turn the light off. So but this switch in the integrated circuit, which is like a kind of silicon wafer, it's actually consists of a lot of units that switch. Each switch is controlled electronically. So so the switch basically, if the switch is actually turned on, then the electron actually, no, you know, electricity can actually pass through. If the switch is off, then it's stopped. Okay, so the control, you can allow the electricity to flow and to stop. So, but it's controlled electronically. So each integrated circuit may contains millions of, or thousand millions of, or even billions of small switch. Okay, so that billions of switch in this integrated circuit basically create this circuit that performs some kind of you know, performs some kind of job. So now when you turn on the switch, then you let the electricity go to flow, and if you turn off the switch, it stops. So this creates some kind of devices called it's not mentioned here, but it's some kind of devices called gates. Okay. So these millions or billions of electronic switch can, put together can create some kind of uh, activity, so eventually you can actually perform the calculations such as like addition, multiplication. So um, so now because of this, so to actually control the circuits, the integrated circuits, you need to actually apply some kind of electricity. You know, um, if you apply the electricity, then you have electricity flow in, and if you actually does not apply the electricity, it's there's no electricity flow in. So in that case, um, we actually call this a digital electronic device. Why it's called digital? Because when the electricity is flowing, then we call this, then we call this actually numbers one, and when it's stopped, it's actually zero. Or you can use the actually voltage to measure these. If there's a positive voltage, we call it one, and if it's actually zero voltage, we call this zero. Okay, so this is actually, so you can see that if you have a electronic circuit, and then you have a whole bunch of input and a whole bunch of output, so we can apply electricity on each of the input. Now if there's electricity applied, then we denote this as 1. And if there's no electricity on this wire, then it's 0. If there's electricity, there's a 1. And no electricity is 0. If there's electricity, is 1. If there's electricity, is 1. And then these circuits are actually doing the calculation based on the control of the switch. You can switch on, switch off, so you can actually eventually generate output. The output could be 1, could be 0, could be 0, could be 1, 0, 0. Okay. So basically this device basically controls the some kind of digital pattern. So you can have an input of certain pattern, and then the device is going to process it and then come out with output, which is another digital pattern, 0, 1, 1, 0. And this 1, 0, 0, 1 is called binary. Okay. So when we say a digital computer, the reason we say digital computer is because computer is an electronic device that processes the binary digitals. Okay, so that's basically when we talk about a CPU is an electronic device that when people actually provide some kind of binary pattern, then you're going to actually process it, and then you're going to generate another binary patterns. And then we human being can interpret each of the pattern and give each of the patterns some kind of meaning. Then we can actually perform various different jobs. Okay, that's basically the computer. So the computer program is basically at the very bottom. It's just like a sequence of binary digitals. That's a computer program, a sequence of binary digitals. So when you actually applied the sequence of binary digitals, the computer system, the electronic device, can actually process this sequence of binary digitals and generate output. Okay. So the early computer system, you will find out they just actually people just directly, create some kind of binary pattern 0, 1, 1, 0, and then they store this binary pattern in the device and then process this data directly. So people actually call this sequence of binary digitals, the machine code. Okay, they call it machine code. The machine code is actually, it's a sequence of binary digitals that the electronic device can directly, you import this sequence of digital code, the computer can process it, do the computing, and then generate output. Okay, so that's the earlier computer language is called machine code. Now, so before I actually continue, then I'm actually going to briefly go over the processors and the memories and all these computer hardware devices. Okay. Now, if you want to know a little bit more, you can read the section 1.5 in the Xi book. Xi book give you a little bit more detailed information about each. So the processors, memories, these are all electronic devices. These are all circuits that perform certain kind of work. Now, processors are circuits that are created to process a list of desired calculation. Okay, so that's the process. With each calculation called instruction. What is instruction? Instruction is also a sequence of binary digitals, like 0, 1, 1, 1, 0, 1, 1, 1. That could represent one instruction, and then 0, 1, 1, 0, 1, 0, 0, 1. That could be another instruction, and then so the computer actually understand each of the sequence of the binary, then perform the task accordingly. Okay. Now, processors, in the past, historically, processors used to take up an entire room, but today, a processor is actually a small chip. When you actually, I don't know whether you have actually make a PC. Have you ever done this? Just purchase all these different components and put them together in a box, and you can make a computer, right? And what the process looks like, it's a small chip. It's a very small, actually, square device, But just remember, in 1940s, for the first computer, a processor actually took the whole office building, And it's made of all these devices called the vacuum tube. Vacuum tube is pretty big, just like a light bulb, and you use actually 1,000 of vacuum tube. For the first computer, they use about 15,000 vacuum tube to wire them together to create this huge processors. Uh, to create this huge processor, and then every time when you run this computer system, all the vacuum tube are going to be actually connected, so they're gonna generate a lot of heat. So that's why you need a very, very powerful air conditioning to cool the computer room down, because the whole process is gonna create a lot of heat. Now, the modern computer system in a small chip, when you actually do the computing job, it can also create a lot of heat, but it's it will be very hot, but it will not compete with the earlier computer system. It's a monster. They're gonna actually consume a lot of power, but modern computer system, actually a CPU, they're gonna take a lot of power. If it's fast, CPU gonna take more power, but they cannot compete with the earlier computer system because the technology has been changed. The memory is another circuit that can store the binary digitals. Okay, they can store 0 and store 1. Okay, now 0 or 1 is our interpretation, but a computer actually, they store the 0 as one kind of state and as 1 as another state. Now, for the most of the hard disk, like a magnetic disk, they use the magnetical plate to actually store the different data, and the one in the magnetic field, and when it's actually going positive, it's represent one, negative represent the zero. So they use different technology to store these numbers. Now instructions are stored in memory. Remember, instruction is a sequence of digitals, 0, 1, 1, 0, because memory stores digitals. So, if one actual memory unit store one digital, then to store an instruction, you just need a couple of actually units to store the instruction. Like in this case, you have 1, 2, 3, 4, 5, 6, 7, 8, 8 digitals. So then you need actually 8 units to store one instruction. Okay. Now each digital, binary digital 0 or 1 is stored in a space, a place called a bit. Okay. Now, so in this case, you need 8 bit. You need 8 bits to store an instruction. If the instruction consists of 8 bits, that's just example. I'm not saying that all the instruction going to be stored as 8 bits, but I just say if the instruction actually use 8 bits, then you need you need actually 8 bits memory space to store this. Okay. Now, sometimes we use different unit. 8 bit is called 1 byte. Okay. So the computer is basically a processor interacting with memory. So processors actually process the instruction. Memory actually basically store the instructions. Okay. So once the actual processor finish one instruction, and then you're gonna actually ask the memory to provide the next instruction. So processor just execute one instruction after another that eventually perform the job. Sorry. So here are some of the sample instruction. So one of the instructions say add X number Y. So basically that instruction basically says add data in memory location X. So the X is memory location. So memory location is also called memory address. So if you have a memory unit, remember each unit can store a couple of actually binary digitals, and then each unit actually is lined up sequentially. So the first unit is the memory address 0. Second unit is 1, 2, 3, 4. Each unit has an address. So when you actually perform the instruction, this particular instruction says add data in memory location X. So if X is 100, that's 100th memory location. Add data in the memory location 100 to the number n, number none. So that's the actual number. Okay. And the storing result in location Y. That's another memory address. Okay. So that means add the data in memory X to the number n. So that means you get the data from memory location X, add the data to the number num, N-U-M. So you basically perform addition, and then you store the result in memory location Y. Okay. Now, one of the example is another, for example, that's subtraction, and that's multiplication, and that's division. And one of the example is like this. If you say MUL 97, number 9, 98. So that means, so you multiply the data stored in memory location. So that's a memory. So you have a whole bunch of location. Now that's 0, 1, 2, 3, 4, 5, 6. That's 97, okay, 98. So then this instruction says multiply the data stored in 97. If the 97 contains the data 3, okay, so then multiply the data in location 97, which is 3, to by num, which is 9 here, okay. So that means what is our operation going to do? You're going to multiply number 3, which is located in memory location 97. Multiply number 3 by number 9. So 3 multiply 9, which is 27, and then store the result 27 into the memory location 98. So that's going to be, so you're going to store the data in there. So this particular instruction basically asks you to multiply the number you take from a memory location 97, which is 3, by 9. So 3 multiplied by 9, and you got the result 27, and store the result 27 in location 98, which is y is 98. So eventually, so you got 98. Okay, so this is actually the instruction going to look like. So when you actually see this, you at least you can see, oh, add sub multi div means division, but in reality, you don't actually, computer even don't understand this. So the actual instruction looks like this. Like I say, it's a sequence of digitals. So this is the real instruction gonna look like. Okay. So for example, 0, 1, 1, this, when the computer CPU sees 0, 1, 1, the computer CPU interpret this as a multiply. And 1, 1, 0, 0, 0, 0, 1, that's the memory address. Okay. And this is actually the number, actual number, and this is another memory address. So this is actually, they use multiply, and this is actually the first memory address. That's a number, and that's another memory address. So, but the computer actually use actual number. Okay. So this is basically the earlier computer system. We use something called the computer instructions. Okay. Now this whole bunch of instruction put together, we call this kind of language the machine instructions. Okay. Now the machine instruction works fine with the machine, but it's kind of difficult for us to understand, because when you actually see this sequence, now if you work in this area, work as a computer scientist, then you know, oh, I know this 001, that looks like an addition, and this is another memory address. So I know this is add the data located in memory location 110001 to that number. And so when you add this number and you got the result, and the result is going to be stored in another memory location over here. So I know this is the instruction. So because I work as a computer scientist. But for other people, if you are not doing the computer science, you're probably going to be confused. What the hell are these people doing? So they just add this number. So that's why in the early age, and the people just view computer scientists are a group of extremely smart people, like a nerd. They can work, and they can talk to the computer. So they can talk the language no one else can understand. So That's the image that the early computer scientists were. So each of these are machine instruction. So later on, people find out this is not really nice. So let's actually create to make it simple, so that when people create this language, they don't actually use the numbers. They use something called a mnemonic code. So for example, 001, that means addition. Now, if I write the computer language, I'm going to say, okay, can I use ADD to replace 001? And then can I still going to use the memory address, still 0111, still use the number, but at least I can use this, you know, some kind of mnemonic form to represent the action I'm going to take. So for like a 0011, I'm going to say, okay, can I use MLU? So now when I see MLU, I know that's the acro for multiplication. When I use ADD, I know it's addition. When I use SUB, I mean subtraction, right? So at least this language is a little bit easier than the machine language. So, and we call this assembly language instruction. So the machine language looks like this. Now, when you actually see this is more or less like assembly language, because at least you can see this. Okay. Now, assembly language is a little bit easier to understand, but assembly language is still actually related to the computer system itself, because in assembly language, you're still going to use the machine, the memory actual location, the memory address. Okay. So which is most people think it's not good. Okay. When I do addition, why I care about the memory location? All I care about is addition, the sum of these two numbers. I really don't care where this number is stored. Store this memory location or that memory location. All I care about is just add these two numbers. So that's why in 1960 and the 1970s, high-level languages for computer system was created. So in that case, when people try to add a two number, they just use, just add these two numbers. So there's no actually such a thing as memory location involved in the addition. Okay. So that's called a high-level language. It was created to support the programming using formulas or algorithm. Okay. So a programmer could write a formula like F equals 9 divided by 5 times C plus 32. Okay. Does everybody know what this formula does?
It
It's actually
translates Fahrenheit to or Celsius to Fahrenheit
that's
or
correct.
something.
Yeah.
Yeah.
Yeah. It's just transfer the temperature from Celsius to Fahrenheit. Celsius is actually the temperature widely used in many other countries, like Canada or other countries, but we use Fahrenheit. So that's the conversion. But when we actually try to do this, if we, this is a very good formula that it's a very good example that the computer can handle this, because when computer handle this, we really don't need to. If I write this using the assembly language, it's very inconvenient, because we have to store the number in the memory location, and then just actually in the assembly instruction, we have to point out which memory location we need to pull the data from. So that's inconvenient. Okay, so that's why high level language becomes popular, Now, the biggest advantage for high-level language is that people who actually write the computer language, they don't need to know the internal structure of the computer system. They don't have to know where is the memory location and the memory address, something like this. Okay. However, the high-level language is really good. However, the high-level language cannot be recognized by computer system because remember, computer only recognize 0101, the binary digitals. So if we write the high-level language, it's easier for us to read, for human being to read it. But if we ask a computer to just say, please compute this, please execute this, I gave you the formula, the computer will never able to do that. So in that case, we need some kind of translator to translate the high-level language into the machine code, the instructions. So these translators are called a compiler. Okay, so we write the code using some kind of syntax, following some kind of grammar, and then the compiler going to actually translate that high-level language into the machine instruction. So that's basically what the compiler going to do. Okay. So the compiler basically convert the high-level language into a machine code. Now, depending on which kind of hardware we use, the machine code are going to be different. Okay. When we actually it depends on what kind of machine you use. If you use the PC with Intel processor, or some people use the PC with AMD, the processors AMD, then the machine code is different. So that means for the compiler need to know, which machine code we need to actually translate to. So, but anyway, this is gonna free the human being from the details of computer. They only need to focus on the computer programming. Okay. And then Java is slightly different. When we use Java, we basically try to make the Java a language that can be run on different computers, the computers with different processor type. Or sometimes we can run Java on different platform. Now, when you say a platform, that means a computer system running on certain type of processor, like an Intel processor, or you can run AMD, the computer with AMD processors. Now, in the past, now some of the machine they use like a Motorola uh, CPU processors, then Motorola has its own set of instructions. So they have a different instruction. But the purpose for Java is to create a language that can run on multiple platforms. What they do is they actually, the Java compiler gonna compile the Java into a type of instruction that instruction can be actually, is based on something called a virtual processor. Okay, it's imaginary processor. It's not real processor. I just I create a kind of virtual processor. I compile the Java so the Java can run on this virtual processor. And then all you need to do is, in order to run on different platform, you just need to actually install the virtual processor on each of the different platform. So as far as the computer support the virtual machine, then it can run Java. Okay. Okay. So now section 1.6, I think I'm going to skip that section, but I still want you to read the chapter So this section basically give you the overview of the computer hardware, the computer history. Okay. So and the computer actually consists of various different peripheral input, output device, storage, memory, um, processors, and also one of the important component in the computer is called in the process is the clock. The clock basically um, uh, it's a processor's instrument. Uh, uh, the speed of the processor is actually governed by the processor's clock. If the clock is faster, then the processor is faster. So when we talk about a computer, a processor like a CPU, when we talk about like a CPU, which is fast CPU, how fast the CPU is, it's a 4 gigahertz. What does 4 gigahertz means? That means the the CPU clock can you know run at the 4 billion cycles per second. Okay, so the clock's speed is very fast. It can run the frequency. The frequency of the clock is 4 billion cycle. So that's 4 gigahertz. Okay, the earlier CPU, which is less powerful, if the CPU is like 4 megahertz, megahertz basically is equivalent to million. It's close to million. So 4 megahertz basically is approximately 4 million cycle per second. Okay. Now 1 hertz basically means a clock X run at the 1 cycle per second. So 1 hertz is kind of slow. If you actually think about this just like a spring, then you can think about a clock cycle is just like the rate of the vibration. So if you actually 1 cycle basically means a second, right? You just 1 cycle. So that means in a second you just run one. Now 2 hertz basically means 2 cycle per second. So that means in 1 second you say ground, run twice. Now if 4 cycle means ground, only run 4 times in a second. But 8 hertz basically means 8 per second. So now you can think about if the speed is faster, then the frequency is faster, so you can run more cycles in a second. If you can run like 100 cycles per second, that's 100 hertz, then you cannot really hear that sound. It's just like a zzz, you can hear this buzz sound. Okay. Now, if you can run like a 1 million hertz, 1 million cycles, that's very fast. Okay. Okay. Now, when I say 1 million cycle, 1 million hertz, it's close to 1 million cycle. But it's not equivalent. When you use the digitals, 1 megahertz basically, yeah, it can run actually about a million cycles. 1 billion cycles in a second. You can vibrate. You can actually run like a million cycle. Now, for each cycle, the CPU gonna perform some activity like get the data the from the memory. So you can imagine if the CPU speed is faster, then in each second it can perform more job. So you can perform 1 billion cycle. If it's a 1 gigahertz CPU, can perform 1 billion cycle. Now each cycle you can perform the activity. So you can perform 1 billion activity. So that means if the instruction requires 4 cycles to complete, if the instruction requires 4 cycles to complete, now with 4 billion with 4 billion with 4 gigahertz CPU, you can perform 1 billion instruction. 1 billion instruction. That's a huge number. So you can imagine how powerful the modern computer is going to be. Okay, so I'm going to skip this computer tour, the 0.7, and just give you a chance to read it. And you still need to read it and finish the exercises in that section. Okay. Now let's actually switch to the computer language. Mostly when we say computer language, we're talking about either the high language or high level language or assembly language. So far, looks like the most popular language is still Java. That's based on a survey of June 2019. Okay, so Java is still takes like a 15% of all the computer programming languages. Then the second one is C, and Python is the third one, but the percentage of Python is growing. So Java is slightly down. So Java actually used to take a lot of percentage, but now the percentage for Java is down. Python is up. Some people predicted that Python may actually continually becomes the most popular language. Okay. And then these are the other language. Okay. Okay, so that's basically the chapter 1. So please actually, if you haven't done so, please complete the chapter 1 so we can move to the next chapter. Now the second chapter, chapter 2, we're going to talk about the variables. Again, I'm not going to actually spend much time on chapter 2 because the variables or assignments, they are very similar to the Python. So if you have taken the CS1, then it's very similar. Now, I'm only going to point out some kind of difference between the Python variables and the Java variables. Okay. So a variable is a named item, such as X. Okay, X is a variable. Number of people, we normally use a variable name like NUM, means number of people, num people. Okay. Each variable requires to have, should have a number assigned to it. Okay. So that requires assignment. Now we just mentioned that the computer assignment is not the same as math equality. In the math, when you say x equals 5, that means the numbers or the variables on both sides of equality are the same. So x is 5, 5 is x. It's the same. But here, when you use a computer language, x equals 5 is a statement. That statement is called assignment. So in that case, x is a variable. Okay, x is a variable. Now, what does variable means? That means when you actually define a variable, the computer actually need to reserve a memory location, or we call placeholder, for that variable. And when you assign number 5 to x, that's called assignment. Now, so that basically means that we're going to put the number 5 in this placeholder that represented by x. Okay, so x represent a memory location, and the 5 basically means x equals 5 means you're going to assign the value x into assign number 5 into x. That means you basically put the number 5 into that memory location. Okay, so the assignment basically assigns a variable with a value. Okay, so that's a different. So in math, you need to know the difference. In math, when you say x equals 5, and I can also say 5 equals x, right? It's basically means same thing. X equals 5, 5 equals x. You can use this interchangeably without a problem in math. But in computer assignment, this is right, this is wrong. You cannot assign a variable to a number. It doesn't make sense because you only assign a number into a memory location. You cannot assign a memory location into a number. What is this, right? So because of this, the nature of this assignment, so some kind of a statement like this makes sense, which does not make sense in math, but in computer science, you can actually have a statement like x equals x plus 1. Okay, this completely makes sense in computer language. Why? Because this is when you interpret this as an assignment, it makes sense. Because if the x plus 1, that means you're going to actually take the value stored in the memory location x. Now, if x is current value for x is 5, then you're going to actually add a 5 by 1. So 5 plus 1, you got a 6. And then you're going to assign the value 6 into the x. So basically, eventually, this statement is going to actually override this value 5 into 6. You remember this? That's called incrementing a variable. So on the right side, so whatever the current value of x is added by 1. And then once the number added by 1, and then you assign this value to x again. So that means you override the current value of x by x plus 1. So that's basically assignment. But when you talk about math, that doesn't make any sense, right? X equals x1. What does that math mean? I can cancel the x on both sides. So I get 0 equals 1. 0 equals 1. That doesn't make any sense. That's not right. So that's the difference between math and the computer assignments. So I'm going to actually quickly go over the chapter 2. So but you still need to, before you do the exercises on each of the chapter problem in chapter 1, like like a challenge activity, and so you still need to you need to do each of the problem in chapter 2. But I'm going to actually go a little bit faster. Now, the second thing is that in computer language, before you use any variable, you need to declare that variable as certain type. So if I actually use the variable x, I want to use the x as an integer. So I need to declare x as an integer in Java. I'm going to say int x. Don't forget the semicolon. Okay. So that means I declare x as an integer. And now once I declare as an integer, then I can assign any integer value to x. So I can assign 20 to x without any difficulty. Okay. So that's the variable declaration. It's a statement that declare a new variable, specifying the variable's name and the type. Okay. So you can say int user age, and declare a new variable named user age that can hold an integer value. Okay. Now, what does that mean? Int basically declare x as an integer. Now in Java, a type integer going to take 32 bits space in the memory. So the integer basically gonna give you, I put the comments after the int. So it's a 32 bits. So that means when I declare x as integer type, then I'm gonna reserve a 32 bits memory space for the value x. So then if it's a 20, then I can store the 20 as a binary number in that 32 bits. So I store this value x. Okay. Now here I need to emphasize the difference between Java and Python. Okay. Now in Java, if you want to declare a type, I'm sorry. I supposed to give you some times to each group have like a group meeting. I'm sorry. I'm running out of time. But I promise that I'm gonna give you the time at the beginning of the next class on Friday. So first, actually, please log into the Friday in the class. Then I will ask you to, you know, split the group so you can have some kind of group discussion on Friday. But not today. It's too late. I'm running out of time. So let me finish this slide and then we'll call it a day. Okay. Now Python is called a dynamically typed language. Okay. Now Java is called a statically typed language. What does that mean? So do you still remember that in Java, if we try to do the calculation, I can say in the Java, I can say x equals 2, y equals 3, and then z equals x plus y, right? And then I can do this. Now, that's totally legitimate in Java, but in Python, in Python, okay. Now in Java, you cannot do this. If you actually type this, even though you're gonna say in Java, you're gonna say x equals 2, you put even you follow the syntax, put a semicolon, y equals 3, semicolon, z equals x plus y, semicolon. This is not right because the Java compiler gonna say x is not declared. Okay, so before you do this, you need to declare x as integer and declare y as an integer. So you can declare x, y in the same line. Okay, you have to declare this as integer before this, and then you can use it. So that's why Java is called a statically typed language. So now Python, when you say x equals 2, what is type of x? Python doesn't, you don't have to declare it because what's the type of x is dependent on what kind of type you need to assign to x. If you assign an integer like a 2 to x, now x is an integer type. Now, next time, after you finish this operation, you're going to assign x equals 2.3. Now, this is actually a floating number, a real number. Then x is a real type. It's not an integer type anymore. So that means the type of the x, you don't have to declare a type. The type of the variable is defined by the data that assigned to this variable. So that's called a dynamically typed. So you can change the type in the run. So when you while run the program, you can always change the type of a variable. But in Java, you cannot do this. Once x is declared as integer, you cannot change the type of x. X is always integer type. Okay, so that's something we're going to continue next time. Okay, so okay, so I'm going to stop right here. So you have any questions?
Is the homework that's due Friday still going to be due Friday, even though we didn't finish the slides?
I still hope you can submit on Friday, but yeah, it's a Friday. It's a Friday evening, like a midnight. So
Okay.
we can still talk about this. Okay, but I hope that you can still work on these exercises, and then if you now you can bring the questions in the class. You know, if I think this question is actually common, then I can discuss this. Any questions you might have. Okay. Any other questions? Let me stop the recording.